Okay, once you identify a probability experiment to be a binomial probability experiment, you can actually calculate the probability of any event very easily with a formula. And here, the following is the formula. Now, this looks kind of complicated here. We have a combinations factor in front. We have P, the probability of success, right? We have a 1 minus P, which is the complement of success, which is failure. And if we're interested in probability that x is equal to some value little x, then this is going to give you the number of successes. And then if there's a total of n trials, n minus x would be the number of failures. Okay. Now, if you go back to that preview example, let's actually go back to that and pay close attention to this. We have successes to a certain power, failures to a certain power, and then there's some number here, right? Some coefficient, number of combinations. Let's go back up to that preview example. Okay, so each one of these probabilities is, so this is a probability that x equals 0, probability that x equals 1, and so on, right? Now let's look at this one here. You see how we have the number of successes, where's one success, right? And number of failures, there's a probability of failures. And then this number here is the number of combinations, number of ways that can happen. Okay. So that's exactly what our formula does. It gives you a number of ways that this can happen times the probability of success to the power of how many successes we're interested in. And then n minus x would be the essentially the remaining amount of trials that are not successful. In this case, the failures. Right? Failures to that power. And again, this will generate, that formula will generate all these probabilities. That's what's so nice about it. It did take us a while to kind of logic our way through all this before, right? Now, once we identify something as a binomial, we're going to be able to come up with these individual probabilities of each outcome very easily. Okay. Oops. There we go. All right. Now, nice thing for us is, yeah, you can do this by hand, and we'll do one example of doing this by hand, but you're not going to have to do this by hand as long as you have a graphing calculator with this function. Okay, and I'll show you how to do that. All right, so before we go on, there are all sorts of ways that questions can be asked as far as they're asking you for certain probabilities, and there's certain phrases that are going to come up. These aren't all of them, but these are examples of some common ones. And there's a mathematical symbol associated with those. So at least or no less than or greater than or equal to is that, greater than or equal to. More than, greater than, does not include the particular number, so it's just greater than. Fewer than, less than, again, doesn't include a particular number. No more than, at most, less than or equal to is less than or equal to. Or exactly, equals, and is just going to be the equality symbol. Okay, so let's do an example here. I'm going to show you this in two ways, using this formula here, and then also using the calculator function, which that'll be the preferred method going forward. I'm just going to show you once with the formula. A student guesses at random on a multiple choice quiz. Okay. There are 10 questions total, where there are 5 choices per question. Okay. What is the probability that a student receives 6 questions correct? Okay. Now, first of all, we have to ask ourselves, is this a binomial problem? Do we have a fixed number of trials? Okay. Well, this person, the student, is basically making 10 decisions, if you think about it, right? So yeah, there's 10 decisions being made, or 10 trials. So yes. Okay. Do we have 2 outcomes per trial? Well, yeah, you can either get it correct or incorrect, right? So yes. Are the trials independent? as long as there's nothing that indicates that they're dependent on each other, we can assume that they're independent. Okay, you don't know if these questions are follow-up questions to a previous question. There's nothing that indicates that, so we can essentially say that they're independent questions. Yes. And then here, this one is actually it's very sensitive to this last question. All right, probability of success the same in each trial. Okay. All right, so the student is guessing at random on a multiple choice quiz. There are 5 choices per question, right? So there's only one correct answer out of 5 choices. So the probability of success in any one of the questions is 1 out of 5, okay? So in this case, yes, right? We'll say that the probability of success is 1 in 5. And it's the same for each question because each of the 10 questions has 5 choices. Now, you can very easily make this a non-binomial. And how would I do that? Well, if one of the questions was like a true or false question where they only have 2 choices, then the probability of success does not remain the same in each trial. So that can very easily be a non-binomial. But in this case, we had 4 yeses, so yeah, we have a binomial. All right, so once we establish that it's a binomial, let's define what our random variable x is. Okay, and it usually comes from the question where they're actually asking for the probability. What is the probability that the student receives 6 questions correct? So that questions being correct is what we're defining to be our variable, really. So let x be the number of correct questions out of 10. Right? So it can range from 0, right, all the way to all 10 of them being correct, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that this is binomial, so x is distributed as a binomial where we have 2 parameters. They're called the number of trials, which is 10. This doesn't change in the problem. And also the probability of success is 1 in 5. Okay, so that's a very well-defined problem now. Now let's actually answer the question, because all we did was just establish our understanding of the question. Okay, what's the probability that the student receives 6 questions correct? Okay, well, let me just kind of show you what's going on here. If we look at since we're dealing with the discrete probability distribution, come up with a table here. All right. There is a probability of having 0 questions correct. 1, 2, 3, 4, 5, 6, ... all the way up to 10, right? And there's a probability associated with each one of these outcomes. Okay. Again, what this formula above does, this formula here, the probability of x equals little x is ncx p to the x times 1 minus p to the n minus x. What this does, it generates every single one of these probabilities. All we have to do is, well, the n and p stay the same throughout the problem. The x, however, does change, right? And if you just plug in 0 for x, 1, 2, 3, all the way to 10, 11 of them, you can actually generate all these probabilities. And keep in mind that all these probabilities do have to add up to be 1. Okay, that's going to be an important thing to consider in the next coming problems. Okay, so if I were to just kind of make a template for this, so we're interested in coming up with this value here, essentially. All right, so let me just kind of make a little template here. They want probability of x equals 6. Everywhere we see an n, we're going to put 10, so 10 combinations. X is 6. P is what, 1/5. X is again 6. 1 minus P, you can probably do that in your head. The complement of 1/5 is 4/5, right? Just 1 minus 1/5 is 4/5. And then 10 minus 6. And you'll see that this is, so 1/5 to, I'm sorry. 1/5 to the 6th, 4/5 to the 4th. Again, these two powers do have to add up to 10 because we have 6 correct, 4 wrong answers, right? And if you do 10 combinations of 10, choose 6 on your calculator, you'll actually get 210. That's from the previous section. I went over how to define that. All right, if you punch this into your calculator correctly, you will get 0.0055 when you round to 4 decimal places. It didn't say to round to 4 decimal places, but typically that's kind of a good rule of thumb for probabilities. Okay, so this would be essentially 0.0055. Okay, again, all you have to do is just change that 6 to any other number with the same p and n, and you can generate all the other probabilities. Okay. All right, now that wasn't too bad, right? You just have to figure out what the n, p, and x are. But there's an easier way, as long as you have a calculator. Okay. Because this probability of x, so you can say or probability of x. In your calculator, there's a function, like TI calculator, it's binom PDF, probability distribution function is what that stands for. Binomial probability or density function. And there's 3 inputs. There's an n, there's a p, and there's an x. Okay. N and p don't change throughout the same problem. So this is 10 and 1 out of 5. And then x in this case is 6. And let me take out the calculator. So all we have to do is go to this menu right here where it says distribution. It's above the vars, right next to the down arrow. Okay. If you do second and then vars, you'll get this distribution menu. Now there's a bunch of distributions that we're actually not going to really talk about too many of these. Some of them we will, like normal CDF and inverse normal, inverse T, stuff like that. We'll eventually talk about, but a lot we don't. We're going to go all the way down until we find something that says binom PDF. Now you'll see that there's two of them, binom PDF and binom CDF. We'll talk about CDF in just a bit. That C stands for cumulative, but we'll get to that in a little bit. All right, so we're going to do this one. The number of trials that we have is 10. P here is 1 divided by 5. And X here is 6. And if you just paste this onto the home... Oh, the other thing is just make sure your home screen is cleared out, because if you paste this onto your home screen and there's anything there already, they might actually multiply with each other and give you something that you don't really want. Okay. One thing to note, like for example, if I didn't know that we had something in the front, you would have to scroll all the way to the left to see. To kind of scroll quickly, if you just press second and then left, you can kind of go back to the left. You see, I notice that there's nothing in front, so I can press enter. But if you go second to the right, you can kind of quickly scroll from the front to the back. So that's just a pro tip there. Okay, press enter. And again, we get that same probability, 0.0055. Okay, so that's going to be the method of choice that we're going to use when we're coming up with these. Now, formula's nice, you know, but if you have access to a calculator, then as long as you understand what you're doing, you know what your n is and your p is. Those are the hard parts, to actually be able to identify something as a binomial correctly, set up the definition for x. Let's do another one here. It says, according to the Air Travel Consumer Report, the largest air carriers had an on-time percentage of 79%. Okay. Suppose 6 flights are randomly selected and the number of flights that arrive on time, x, is recorded. Okay. Find the probability that at most 2 flights arrive on time. Okay. Again, do we have a binomial here? All right, do we have a fixed number of trials? Well, 6 flights are randomly selected and the number of flights that arrive on time is recorded. Okay, find the probability that 2 flights arrive on time. All right, so we're choosing 6 flights at random, okay, and we're just trying to determine whether they are on time or not on time, right? Because some of them, there's a 79% chance of being on time. All right, so let's just say that. So yes, we have yes, and in this case it's 6. Okay, you have 2 outcomes. Well, yes, you can either be on time or not on time. So yes. Are they independent trials? Independent trials. Well, as long as the flight, like if you're talking about a flight and then the flight right after shows up, one might actually affect the probability of another showing up on time if they're just like in sequence or something. But the fact that we're randomly selecting them, then that essentially eliminates that, right? We're randomly selecting them, so essentially they don't depend on each other. And then does the probability of success the same in each trial? Right, a trial is a randomly chosen flight, and the probability of success, so according to, usually this is given by some sort of predetermined survey or some sort of statistic. In this case, they know it's 79% chance of being on time. So yeah, in this case p equals 0.79. So we have the n and your p there. So you do kind of want to go through this process to essentially, for one, to identify the binomial, and also to identify your n and your lowercase p. Right, they say that the x is the number of on-time flights. Right, they actually already defined that for us. Right, the number of on-time flights out of 6, and we know it's binomial, where n equals 6 and p is 0.79. Now we can answer our questions. The question is, find the probability that at most 2 flights are on time. Well, can there be any more than 2? No, right? At most it's 2, but it does include 2, right? So it's less than or equal to 2, right? Probability that x is less than or equal to 2. Now, this could be done in a couple of ways. Okay, probability that x is less than or equal to 2. Well, if we look at the table here, x, probability of x, 0, 1, 2, 3, 4, 5, up to 6, right? And there's a probability associated with each one of these. We're looking for essentially 0 through 2. We're looking for all those probabilities. You see that? Well, how can you do this? Well, we can essentially add up probability of x equals 0 plus probability that x equals 1 plus probability of x equals 2, right? And then you can do a binom PDF for each one of these, right? Again, n would be 6, p would be 0.79, x for this one would be 0, right? That's your npx. Let me just label those, np and x. You do it for each one, right? I might run out of space. Try to draw a little smaller. N, P, X right here would be 1. And I'm going to run out of space here. Binom, PDF, N, P, and then the last one's 2, right? 0 goes with 0, 1, 1, 2, 2. The N and P stay the same throughout the problem. Okay, so we have the distribution here. Function, binomial PDF. All right, we have 6 trials. Oh, again, if you needed to know how to do this, if you don't have this menu, you have to do binomial PDF 6, like if you have a TI-83, and you do comma, which is above the 7, and then 0.79, comma, 0. Okay, and then enter, and then you'll get the same thing that we have. 0.79, 0, enter. Okay, so you'll just have to do it like that. If you have a TI-83, you'll know what I'm talking about. If you have a TI-83, 6, comma, 0.79, comma, 0, and then press enter. So that first one, okay, that's a really, really small number. So that's it's in scientific notation. It's a very small number, right? But if you wanted to come up with the one with 1, if you go back up, you can kind of recall that. Or if you have a TI-83 that you can't do that, if you just press second and then enter again, it recalls a previous equation. And then you can just go over to the 0 and then edit that to a 1. And I'll give you that. And then you can do second enter and then edit that to a 2. Okay. Now that's basically 0 if we're rounding to 4 decimal places, right? Because that's times 10 to the negative 5. But if we add these two numbers, then we should get what we actually want. Okay. Again, if you have one of these calculators where you can just kind of go up and scroll to highlight one and then add on the next one, or just copy the first 4 or 5 decimal places over and just type those out and then add, because we're going to round to 4 decimal places anyway. You get point, you know what, and I'm also going to add on I think this might add something to it. Let's see. Yeah, it does make a difference actually. Not much, but a little bit. So we have ourselves 0.0202 if I'm rounding. Okay, so now you can see how that can be pretty tedious, especially if you had like an n equals, let's say, 20, and you're doing probably the x is less than or equal to 14 or something. Then you would have to do 0 plus 1 plus 2 plus 3 all the way up to 14. So you can see how that can be pretty tedious, right? Now, lucky for us is that our calculator does actually have a specific function for less than or equal to. Okay, so probably the x is less than or equal to is not binomial PDF, but binomial CDF, cumulative probability function. Okay, binomial CDF. So that's the key difference there. What this does is it adds up everything starting from 0 all the way up to the specified number. So it still has an NPX, which is 6, comma 0.79, comma, in this case, 2. And if you put that in your calculator, again, let me show you how to do that. Okay, so if you put that in your calculator, let's clear out my screen, second distribution, go down to binomial CDF this time. Same inputs, 6, 0.79, 2, paste, enter. Again, you get the same number, 0.0202. Okay, and here are the ways to find everything that we just talked about. Okay, now we did probably x is equal to something, and then probably the x is less than or equal to something, and we know those as binomial PDF. Less than or equal to something is binomial CDF. For anything other than those two, then we have to kind of be careful with. Okay, so if it's less than a certain number, probably the x is less than a certain number. It's probably binomial CDF NP x minus 1. So for example, probably the x is less than 5. What that really means, that's probably that x is less than or equal to 4, right? So that means it's just binomial CDF NP4, right? So that's all that means. Greater than or equal to x. Well, this is kind of a weird one, and I'll have to kind of show you. It's best to show you with a table. Okay, I almost I never refer to these. I always use a table to kind of logic my way through all this stuff, and which is what I'm going to show you on the next example. Okay. All right, use your calculator to find the following binomial probabilities. Write down the math symbol and the calculator command used. Okay. According to Experian Automotive, 35% of all households have 3 or more cars. Okay. A random sample of 20 households will be chosen. Okay. Okay. First of all, do we have a binomial here? And they kind of already tell us that it is, but let's just confirm that. Fixed number of trials. Well, we go up to 20 households. Do we have 2 outcomes per trial? Okay. They're going up to households and essentially trying to figure out if they have 3 or more cars, right? Apparently from some prior study, Experian Automotive, 35% of households have 3 or more cars. Okay, so there are 2 outcomes. Either you have 3 or more cars or you don't. Or you have less than that. So again, yes. This one's a yes also. Independent trials. A random selection of 20 houses are chosen. So yeah, they're independent from each other. If they're randomly selected, right? The response of one household isn't related to the response of another household if they are randomly selected. And then probability of success is the same in each trial. Probability of success, the same. Each trial, yeah. There's a certain 35% chance of a randomly selected household having 3 or more cars. So yes. 0.35. Okay. So let's define a random variable x. Let's let x be the number of households with 3 or more cars out of 20. Okay, we know that this is a binomial because it met all 4 criteria, where n is equal to 20 in this case, and p is equal to 0.35. Okay, now that our random variable is well defined here, it's the number of households with 3 or more cars out of 20, then we can start asking all sorts of questions. So we are good here, A through D. Okay, so the first one says, what's the probability that less than 4 households have 3 or more cars? Okay, probability that less than 4 households. Probability that less than. So does that include 4 houses? No, less than. So the way you want to write this is probability that x is less than 4. Well, since this is a discrete probability distribution, less than 4 is the same thing as probability that x is less than or equal to 3, right? That means exactly the same. Less than 4 means less than or equal to 3, because there can't be any partial households, right? This is a discrete random variable. And we know that for less than or equal to, that's just binomial CDF, where you have your n, your p, and your x. Your n in this case is 20, your p in this case is 0.35, and your x is 3. You punch that into your calculator, just like the way we did before, and you get 0.0444. Okay. What's the probability that at least 4 households have 3 or more cars? Okay. At least. So can there be less than 4 households? No. 4 or more, essentially. So probably that x is greater than or equal to 4. At least 4. Okay, so this is where I kind of want to show you that, yeah, we have that table above that can show you exactly what to do here. But I want you to think of it in terms of that probability distribution table. Okay, this will help you at least get some sort of visual for what we're doing. All right, so again, our x random variable ranges from 0 all the way up to 20. Okay, so 0, 1, 2, 3, 4, 5, 6, dot, 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 all the way up to 20. Okay, and what are we actually interested in? Probably that x is greater than or equal to 4, right? So here's 4, right? So we want all of this. Okay. Well, what do we know for in a probability distribution that the sum of all the probabilities add up to? Well, we know that the sum of probabilities of x equals to 1, right? We are interested in this, probably that x is greater than or equal to 4. Okay. Now, if we're clever, well, if we're not clever, what we'd do is, well, we'll say, well, there's only two functions, right? There's a binomial PDF and binomial CDF. CDF is for less than or equal to, okay? What we can do is you would do binomial PDF for 4, 5, 6, all the way up to 20. That would be very tedious. You'll get the right answer. It'll take a while. Or it can be clever, okay? Because we know that all of these have to add up to be 1, right? So if we were interested in this portion, and what do you think this portion is right here? Well, isn't that the probability that x is less than or equal to 3? X is less than or equal to 3. Right? So these two add up to be 1. So doesn't this make sense that if I wanted to just have this, wouldn't I just say 1 subtract off that first part? 1 minus probability that x is less than or equal to 3. Okay. Which is exactly what we want. 1 minus probability that x is less than or equal to 3. And for things that are less than or equal to, well, we have a function in our calculator that's called binomial CDF. Binom CDF. N, again, 20, and P is 0.35. That doesn't change throughout the problem. X in this case is 3. And we can also, again, reuse this calculation from before. I typically don't like to do that, even though I can just do 1 minus this number and get my answer. But again, that could have been a rounded number. So just for the sake of the example, let me show you how to actually put this into your calculator. All right, so we want to put it in just the way we see it. So let me clear out the home screen. If you do 1 first, and then we can subtract, and then we go to the second distribution. Go down to binomial CDF. You have n is 20, p is 0.35, x is 3. We're going to paste that on. Okay, if I just do second to the left, you'll see that there's a 1 minus in front, second to the right. And let's just press enter. And then you'll get this answer, 0.9556. Okay. Again, what's the probability of that 2 or 5 or 6 households have 3 or more cars? They're literally just saying what's the probability that x is equal to 2 or x is equal to 5 or x is equal to 6. These are OR probabilities, okay? And they're all disjoint from each other. Probability that x equals 2 plus probability that x equals 5 plus probability that x equals 6. There's really no way around this that you can do. Again, if you're looking at the distribution table here, just to kind of do a quick sketch of what we're doing: 0, 1, 2, 3, 4, 5, 6, 7, dot, 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 20. We're only interested in this guy here, this guy here, and this guy here. Each one of those is a binomial PDF. So let's do that. Binom PDF NPX, N is 20.35, 3. I'm sorry, that's a 2. Plus binomial PDF 20.35, 5 plus binom PDF 20.35, 6. All right, if you punch those into your calculator individually, and when before getting my final answer, I usually like to round to 5 decimal places instead of 4. So if you did that, 0.00998, 0.12720, and this one would be 0.17123. And then when you add these up, and then I like to round. Okay, you get 0.3084. So it's about a 31% chance that if you go up to 20 houses, there either be a 2, 5, or 6 houses that have 3 or more cars. About 31% chance of that. All right, we have 2 more. What's the probability that at most 10 households have 3 or more cars? At most. Probably the X is at most 10. So that's less than or equal to 10. All right, this is basically an easy one. That's just binomial CDF, right? Nothing crazy there. Yeah, so you want to be able to recognize less than or equal to is just binomial CDF, and then equal is binomial PDF. Okay. That's 20. Again, your N and P don't change throughout the problem. Your P is 0.35, right? Your X here is 10. You punch that into your calculator, you're going to get 0.9468. And then the last one here. Okay, so this one is actually quite interesting. Okay. So it's a weird one. Okay. It says, what is the probability that between 10 and 15 inclusive, meaning that we're including both 10 and 15, households have 3 more cars? Okay, so you have to be a little clever on this. There's a couple ways to do this. Okay. And I'm just going to do one way, but I'm going to kind of talk you through the brute force method of doing this. But again, if we had a table here, again, this table here isn't really required for the problem. It's just more for illustrative purposes, just demonstration purposes, really. All right, again, our table runs from 0 all the way up to 20. So, and I want to include 10. I know I'm not going to draw them all, but 1, 2, ... 8, 9, 10, 11, 12, 13, 14, 15, 16, ... 20. Okay. I was running out of space there. All right, we're interested in 10 through 15, right? We're interested in here to here. That's what we call probably that. Well, in symbol format, the way you write that would be this. Probability that X is between 10 and 15. That's how you would write that in symbol format. So probably that X is between 10 and 15. Okay. Now how would you do this? Well, one way is just to do binomial PDF for all 6 of these, and then you're done. 10, 11, 12, 13, 14, 15. You can do that. You get 6 terms, add them all up. Kind of like what we did up here, right? But it can be a little bit more clever. Okay. Well, we know what? Well, we know we can use less than or equal to, right? And that's a binomial CDF, right? From 0 to 15, all of this, I'm going to write over this. All of that is probably that x is less than or equal to 15, right? 0 all the way up to 15. All of that is that, okay? And the stuff right down here, well, less than or equal to what? 9, right? So if this is less than or equal to 9 plus the green portion adds up to be this, less than or equal to 15. Can we do a little bit of subtraction here? Because we can say that probably that x is less than or equal to 15, right? Which is this portion, minus this portion, leaves us with this portion. Does that make sense? So probably that x is less than or equal to 15, right? Which is everything 0 through 15. And then we have to remove 0 through 9, which is probably that x is less than or equal to 9. Okay, and again, these are both binomial CDFs. So this is the clever way of doing this. You have NPX minus another binomial CDF. NPX, that have different x's. This will be 15, that will be 9. We have 20.35, 15, 20.35, 9. If you run both of those, oh, this is binomial CDF. Okay, now if you run both of those through your calculator, you're going to get this. Again, I like to round to 5 decimal places. That one's pretty close to 1 already. Subtract those and you're left with about 12%. Okay, one last thing here. Again, there's another advantage to knowing if a probability experiment is a binomial probability experiment, and that is computing the mean and the standard deviation. Because typically, to calculate the mean or standard deviation, the mean is the sum of x times probability of x, which we can do, right? If we have a table of values, you can do x times the probability of that value plus the next row, row by row, right? But if you know something is binomial, then calculating the mean and standard deviation is very, very easy. It's just n times p for the mean, and then n times p times 1 minus p, the square root of that, would be the standard deviation. Again, p and q, 1 minus p and q are sometimes, some textbooks just call that q. Yeah, q is just 1 minus p. But there's really no need to introduce another letter if it's related to something that we already know, which is p. Okay. All right, so let's see how this performs, or how easy it is to calculate this. Now this formula here for the mean should be intuitive. This is not as intuitive. Example 5. A student guesses at random on a multiple choice quiz. So just like that previous example. There are 10 questions total, where there are 5 choices per question. Find the mean and standard deviation. Okay. Again, this is a binomial, just because it's from the previous round that we did, so we don't have to go through those 4 steps. And the mean here is calculated just as simple as n times p, right? Now, if you were to take a guess, again, if there's a 1 in 5 chance of guessing an answer correctly, guessing a question correctly, and you have 5 questions on the test, then you should expect to get 1 out of those 5 questions, correct? Now, if you have 10 questions, so that should be scaled up, right? For every 5, you get 1 right. So for 10 questions, you should get 2 right on average, right? Let's see if that's true. Okay, if n is 10, and p is 1 out of 5, right? That was your n. That was your p. 10 divided by 5 is 2. Yeah, so on average, you expect to get 2 of the questions right. Now the standard deviation is the square root of np times 1 minus p. again, our n was 10, our p was 1 out of 5, our n, or 1 minus p is the complement of 1/5, which is 4/5. Right? Square root of, what, 10 times 1 times 4 is 40, 5 times 5 is 25, and if you put that into your calculator, square root, let me just show you that on the calculator. Okay, to get the square root symbol, you just do second, and then it's in blue right there, it's x squared, and then you can just do 40 divided by 25, enter, and let's just do like 2 decimal places, or 1 decimal place really, about 1.3. Let's do another one. You roll a die 10 times and count the number of ones. Find the mean standard deviation. All right, again, the n and the p have to be identified first. Roll the die 10 times, so n is 10, and the number of ones is what we're looking for. So again, in a die, there's 6 sides to a die. I'm assuming this is a 6-sided die. So the probability of getting a 1 is, well, there's 1 out of 6. Okay. Again, let's find the mean value. Mu equals NP. 10 times 1 out of 6. Which, if you just put that in your calculator, I'm just going to round to 1 decimal, about 1.7. Or the number of ones that show up is 1.7. And the standard deviation here is square root of np times 1 minus p, which again is equal to square root 10 times 1 out of 6. And the complement of 1 out of 6 is 5 out of 6. 10 times 1 times 5 is 50 in the numerator. 6 times 6, 36. If I put that in my calculator, 50 out of 36, I get about 1.1. But the next thing is to just kind of show you how probability histograms look like for binomials. Okay. Now we know for a table, you have all those probabilities associated with each outcome, right? And some probabilities are greater than others, right? So if you create the table, so for example, this is n equals 25. So this is essentially 0 through 25 are the possible outcomes. And you notice that you don't see much of a height anywhere around here, right? There is a probability associated with each one of these. They're just very, very, very low. Okay? Just a very small probability of occurring. Okay? Now when you start having a substantial probability of occurring, it's somewhere around, I don't know, around 14, 16, so forth. There seems to be like a center, right, to this distribution. You start to notice that you have this bell shape, right? It's not completely symmetrical, but it's pretty symmetrical. And what would be the center? Well, we know that the mean here is n times p. N is 25, p is 0.8. If you were to calculate that, you should get 20. So here's 20. That seems like it's the mean. Yeah, that box right there is 20. This box right here. Okay. All right. What happens if we just increase this to 50? Well, mu equals n times p, which is 50 times 0.8. 80% of 50 is 40. 40 seems to be around here. Around here is 40. 40 seems to be around here. So that seems like to be like the center there. And again, you start to see that kind of bell-shaped thing going on right there. And then again, let's just move it up again to 70. Mu equals np, which is 70 times 0.8. If you multiply those out, you get something like 56. Again, 56 seems to be somewhere around here. again, as we increase n, it starts to become, well, it already looks pretty bell-shaped here, but over here, the left side and the right starts to become a little bit more symmetrical. Okay, the spread starts to look about the same on both sides here. Okay, if you have something that's bell-shaped, that's a nice thing to have. But we also know about a rule called the empirical rule, right? That's a 68, 95, 99.7 rule. Okay. Now, we're going to be using the mean and standard deviation for a binomial and use the empirical rule. Now, under certain conditions, a binomial will look bell-shaped like this. Sometimes it won't. Okay, there are certain situations where it'll look way too skewed to one side or the other, so it won't look like a bell-shaped curve. Okay, and what are those conditions? That basically a threshold that tells us that we can use the empirical rule. Well, that's if np times 1 minus p is greater than or equal to 10. Okay, if that's the case, so if we know the n and the p, we can calculate this quantity, and if it's greater than 10, then that means we can use the empirical rule, which is that 68, 95, 99.7% rule. Right? Within one standard deviation, 68% of the data is there. Within two standard deviations, 95%, and within three standard deviations, 99.7. Okay, and we're going to consider something to be unusual if it lies beyond two standard deviations. So anything usual would be the first two standard deviations, which is representing 95% of your data. Anything outside of that is the remaining portion, 5%. 2.5% on one side and 2.5% on the other side. All right. Example 7. According to Experian Automotive, 35% of all households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. All right, so this is kind of a prelude to what we're going to talk about in a few chapters from now. And that's going to be hypothesis testing. Okay, there could be some sort of statistic out there that could be challenged, right? Like in this case, a researcher believes this percentage is actually higher than this 35%. Okay, well, how do you challenge something? Well, you're going to have some sort of evidence to kind of persuade somebody to think otherwise, right? So in this case, he conducts a simple random sample of 400 households and found that 162 of them had 3 or more cars. Would this result be unusual? Well, he did say that the percentage is more than 35. So just based on his sample here, what would be that percentage? Well, 162 out of 400. Let me just get an approximation here. 162 out of 400. Well, he gets... Actually, this is not approximation. This is exact. About 0.4... About 40%. 40.5%. Which is higher than 35%. But how can you tell if this was kind of a fluke, right? You can't tell if that 162 is significantly higher than what it should be, okay? And what should it be? Well, what do we expect it to be if 35% of all households out of these 400 are actually have 3 or more cars? Well, we expect it to be N, which is our 400, times P, okay? 400 times 0.35. We expect that to be about 140, right? That's what we expect to have as far as the number of households that have 3 or more cars out of 400. 35% of that is 140. He got 162, but we have to somehow figure out if that's unusually high. Okay? Because if he did actually sample this correctly, he didn't cherry pick the houses, right? Then we might have some evidence to support his claim that it probably isn't 35%, but maybe something higher. Okay, that's going to be something in the future that we're going to talk about when we get into hypothesis testing. All right, so how do we know if something's unusual? Well, if it follows this bell-shaped curve, it's going to follow this empirical rule. So we have to talk about being outside of 2 standard deviations from the mean. Okay, but before we go on to that, let's see if we can actually use this normal approximation. Can we use empirical rule? Bell shape, question mark. So we have to do np times 1 minus p. It has to meet this criteria to see if it's greater than 10. And n in this case is, this is 400. P is 0.35. 1 minus p is 1 minus 0.35, which should be 0.65. If you calculate this, let's see what we get. 400 times 0.35 we get 91, which is greater than 10. Okay, that means we can continue with this problem. Okay, let's come up with the standard deviation. Times 0.35 times 1 minus 0.35. That's just 0.65 if you just want to do that mentally. So square root 400 times 0.35 times 0.65. You're going to get about 9.5 if you're rounding to like 1 decimal place. You only really need 1 decimal place. Because we're going to start using the empirical rule here. Let's go ahead and draw a number line here where the mean is at the center, and we're going to add on a standard deviation and then another one, and then subtract 1 off. Alright, the mean is 140. Okay. If we add 9.5 to that, that brings us to 149.5. Add another 9.5. That's 159. And then just to be complete, let's go this way. We get 130.5, and then subtract off another 9.5, we get 121. All right. Now, anything beyond 2 standard deviations, so everything here and here are not unusual. These would be unusually high results, and this would also be unusually low results. So if you go up to 400 households, 95% of the time, you'll come back with anything between 121 and 159 to be the number of households that have 3 or more cars, according to that 35% statistic that Experian Automotive claims or suggests, right? Well, he came back with 162, or what's 162? Well, 162 is around here, right? That's in that unusual range. And if he actually sampled correctly, meaning which is a simple random sample, there wasn't no cherry picking or any biasness going on. So maybe he has some sort of evidence to suggest that, yeah, maybe it's not 35%. Maybe it is a little bit higher. So that's what we're going to get into when we start talking about hypothesis testing in a couple more chapters from now. If there's a claim that's being made, can somebody counter that claim with some sort of evidence? Okay, that's where this whole class is leading to.